Hello, everyone. We are going to get started on our last section of the course. And I'm going to do a couple of videos. It's a big section. Vectors are something that are so applicable in the real world. A lot of trigonometry, most of trigonometry, is very applicable in the real world. So let's talk about some things called vectors. Now, a lot of what we learn about with vectors will feel very similar to things we've done throughout the semester. So you're going to review some things that we looked at with polar coordinates. You're going to review some things we looked at in algebra, and it all ties in together with vectors very well. It won't seem so foreign to you. But first of all, let's just talk about what's a vector. A vector is a directed line segment, which has both magnitude and direction. So for example, if you start at one point and head towards another location or another point, that's a vector. We use an area to illustrate the direction of the line segment. Now, it could look a lot of different ways. This one's going up and to the right. When we graphed lines, that would be a positive slope. You could have something going down to the right. You could have something going straight down. You could have something going backwards. You could have something going backwards and up, backwards and down. Infinitely many ways that we can write vectors as we go through and look at things, right? These are all vectors. So they go on forever, all kinds of different possibilities as you go. Now, one thing about a vector is every vector has a start and an end. This point where we're starting, or what's also referred to as the tail of the vector, is the initial point. What is our starting point? What is our initial point? Sometimes, again, you might hear me say tail of the vector. This point over here is the end of the vector or the head of the vector, okay? And this is what we call the terminating point, okay? Every vector has a location where it starts and a location where it ends. For example, look at this graph below. We have a vector that is starting at the point -2, -1. This is our initial point. -2, -1 is our initial point, the tail of the vector, okay? And the arrow is pointing towards B. This is our ending or our terminating point. That point 2, 3 is our terminating point, or the head of the vector. The direction, where's it going? Where's it heading? Think of it like that. So that's an example of a vector. Now, notation-wise for vectors, lots of times we use a lowercase letter like a lowercase v for vector. We can also write a vector with the letters of the points. So we have the initial point A, the terminating point B, the tail and the head, and we put the arrow over top to represent that we're talking about a vector. Both of these guys are very accurate ways of writing that, okay? Just like when we were graphing lines, we're always going from one point to the next. And notice, no matter which vector we have, think about how you're going from one point to the next. This one, we're going up and to the right. This one, down to the right. This one, straight down, straight backwards, backwards and up, down and backwards. We can think about the horizontal direction and vertical direction as we go through. If you imagine that left-right movement, how do you move from left to right to get from one point to the other? That horizontal direction okay? This is what we refer to as the horizontal component. So imagine if I start at this point A, and so to move horizontally, do I need to go left or right? I need to go to the right. So I'm going to dash in here my right movement, and I'm going to go to the right until I get to 2, okay? This distance right here is my horizontal distance. I went horizontal, direction was to the right horizontally, horizontal distance. And I went to the right 1, 2, 3, 4 units. Okay. I went to the right 4 units. Well, think about our x values. If you go to the right 4 units, our right direction is more positive. Going left is more negative. Left is considered a negative direction, right's considered a positive direction. So my horizontal component for this guy is a positive 4. You don't need to write the positive, it's just 4. We went to the right, the positive direction, 4 units. That's a horizontal component of 4. Now, we can also talk about the upward movement, the upward or down, up and down. What's happening vertically? What about our vertical distance? Okay, this is going to be referred to as our vertical component. So I've moved to the right 4 places. Now what do I need to do? I need to move vertically to get to that end point. How far? I went vertically 1, 2, 3, 4. I went up 4 units. Now again, up and down. If you're going downward, that's a negative direction. That would be a negative movement. If you're going upward, positive direction, that's a positive movement. So the fact that we went up 4 units means that's a positive 4. Our vertical component is positive 4. I'm going to write VC for vertical component. Anytime you want to find your horizontal component or your vertical component, and every single vector has a horizontal component and a vertical component, it is really important about the order, okay? Because the direction definitely matters. Left is a negative direction, right's a positive direction. So the signs are going to matter here. That's like what we did with rise and run when we were dealing with slope and things like that. What you're going to do in order to get every single time, let's look at what's happening here. One way that I could have gotten this, I had an x value of -2 and I ended at an x value of +2. Notice if I had gone my second x value minus my first x value, that would have been 2 minus a -2. 2 plus 2 is 4. Okay? Could have done the same thing with my y values when I'm talking about this vertical difference. Okay? My second y value, my first y value, if I went y2 minus y1, I have a +3 minus a -1. That's a 3 plus 1, which is 4. Okay? You can always get, no matter what points you have for any vector, okay? You can always get your horizontal component by the difference in your x values. It's your x values that are left and right. This x value comes from the end or the terminating point or the head of the vector. This one comes from the tail. So terminating minus initial x value. Vertical component is going to be the difference in your y values. Same thing from the head and the terminating. And what we call the component form of a vector, we can write any vector using this notation. Okay, we have this symbol You write whatever the horizontal component is, comma, the vertical component, and this symbol, okay? Kind of like the less than, greater thans, pointed edges instead of ordered pairs, but it is horizontal component, x's and y's, difference in x's and y's. It's a distance, the horizontal distance, the vertical distance. For our last example, that means that that vector AB or vector V in the diagram, I put a V there. In component form, we write that as 4, 4 with the less than, greater thans around it, okay? The thing about vectors, as we go through and look at these, notice if you know your initial point and your terminating point, that's a very specific vector, okay? When you see component form is horizontal distance, vertical distance. If you only see the component form, you're going to know, basically it's telling you how long the vector is horizontally and vertically, but we're not going to necessarily know exactly where it starts or exactly where it ends, okay? Let's go ahead and look at some examples here. So let's look, for example, remember, component form, difference in x's, difference in y's. This is my horizontal component. This is my vertical component, okay? I want to find the component form of this vector. I have vector v. I'm given that the point P is 2, 1.5. Point Q is 5, 6. It's important we know where the vector is starting, where it's ending. So we know this is the initial point or the tail. This is the terminating point or the head of the vector. So as we go through to find this, our horizontal component is going to be the horizontal distance, the difference in our x values. Now, if you have a graph, you can look at it graphically. I threw a 1.5 in here for a reason, because you can't always just count. What if you had fractions? What if you had gigantic numbers and you didn't want to look at this as the graph? You don't always have to have the graph as long as you know the points. So the difference in your x's. So the head or the terminating point is 5, 6. The x value, so that's my x2 and y2. So my terminating x is 5. My initial x is 2, and 5 minus 2 is 3. I do my vertical component. That's the difference in my y values, the vertical distance, the rise. My terminating y value is 6. My initial y value is 1.5. So I have 6 minus 1.5. That's a 4.5. So what's that tell us about the component form of this? This vector v in component form is the vector where the horizontal distance is a positive 3, the vertical distance is a positive 4.5. And what that means is, starting at the initial point, a positive 3 means you need to move to the right 3 and up a positive 4.5 and up 4.5 to get to the end of the vector. We're going eastward and northward. We're going right and up when they're both positive, more positive direction, okay? Let's look at example 2. We want to find the component form of a vector with the initial point of 2, -1 and a terminating point of -3, 8. We don't have the graph, and I'm not going to draw the graph, but think about a few things here. Notice my x values. I'm starting at 2. I'm ending at -3. So what's happening with my x's? I'm starting at a positive 2. I'm ending with a -3. I'm going to the left. I'm getting smaller with my x's. I should have a negative horizontal distance. Okay, horizontal component should be negative. My y value is a -1 to a positive 8. I'm going smaller to larger. So what's happening is I'm getting more negative but I'm getting higher. So my vector is going to, if I wanted to graph it, my vector would kind of have that look to it. But you don't have to graph it. Your horizontal component is going to be the difference in your x values, but you always start terminating first, terminating or head of the vector first. So I have a -3 minus a 2. -3 minus 2 is a -5. Notice I am getting more negative. A negative refers to going in negative direction. Vertical component, terminating points in 8. So I'm going to start with the 8 for the y value, minus the -1. That's an 8 plus 1, or a 9. So this vector, this point PQ, has a horizontal component of -5 and a vertical component of +9. If we start at the initial point, we have to go backwards 5 units and up 9 units to get to the terminating point. This is called the component form. Okay? Look at example 3. Find the component form of a vector with an initial point of 4, -2, oops, and a terminating point Q of 4, 5. So let's look at what's happening here. This is the initial point, or the tail of the vector, the terminating point, or the head of the vector. So remember, horizontal component, the x value at the end, the head, minus the x value at the tail. Terminating minus initial. So my x values, terminating x is a 4, minus initial x is a 4. I have 4 minus 4, which is 0. I started an x value of 4 and I stayed at an x value of 4. I'm not going to the left or the right. Okay. Our vertical component, the y value at the head, or the terminating y, minus the y value at the tail, or the initial y. Y value at the terminating point is a 5, minus the initial y value is a -2. 5 minus -2 is 5 plus 2, which is 7. That means that this vector, PQ, is a vector with a horizontal component of 0 and a vertical component of 7. Okay? Imagine what that would look like. You're starting at an initial point and you're not moving left or right, but you're moving up. That's what that vector would look like. Okay? So no left, right, east, west direction, no up, down, north, south direction. You have a couple of problems to try in your notes, so why don't you go ahead and pause the video and give these two a try. Find the component form of the vectors with the initial conditions, initial point -3,9, terminating point 3,5. Do the same thing for a point with initial point -2,3 and terminating point 12,3. So go ahead and pause and do it. Come back, check it, or fast forward to the next part if you have it. Okay? All right. Horizontal component, difference in your x's. This is your terminating x, or your head. So that's going to be a 3 minus the -3 is 3 plus 3, or 6. Your vertical component is the 5 minus 9. 5 minus 9 is -4. So this vector, PQ, has the component form of 6, -4. If we start at the initial point, we're needing to go to the right and then down. The next one, horizontal component, remember, and vertical component. Remember, always start with the, when you do the difference, with where you end minus where you start. So we're ending with an x value of 12. We're starting with an x value of -2. 12 minus -2 is 14. We're ending at 3, subtracting the starting y value 3. 3 minus 3 is 0. So this vector, PQ, in component form is 14, 0. With this one, when we have the initial point P, we're starting and we go to the right 14. We get larger by 14, but we don't move up or down at all. So this looks kind of like a horizontal line, except it is directed. Okay. Let's go ahead and talk about the next part of vectors. Definitions. Every single vector has a length. Every vector can be defined by its length. This distance from A to B is its length. The length of the vector is what we refer to as magnitude. So you'll hear me talk about magnitude quite a bit in this video. Let's look at the first vector we saw. A rough sketch of it, we have that point A, which is -2, -1. That's the initial point. B is the terminating point, 2, 3, okay? When we talk about magnitude, first of all, we went through now, as far as distance goes, what do we know about this vector? We know its horizontal distance, okay? And we know its vertical distance. We know that its horizontal distance, or its horizontal component, is 4. We did that in the first problem, so we know that that distance is 4. We also notice that its vertical distance, or its vertical component, right here, and this is not a great sketch, it's not to scale, but that is also, we calculated that to also be 4. Notice when I sketched in my horizontal distance and my vertical distance, what happened with this diagram? I ended up with a right triangle. Now, we've dealt with right triangles a lot in trig, right? And we've dealt with right triangles a lot in a lot of situations. We get a right triangle. We're looking for the length or the magnitude of this line segment, of this directed line segment of this vector. That is this side right here, okay? This length is the magnitude of that vector. We want to find that length. What are we wanting? We're wanting to find the hypotenuse of a right triangle. How did we do it? Pythagorean theorem, right? Pythagorean theorem. We have a right triangle. So if you square each of your legs and add them together, you're going to get the square of the hypotenuse, right? Each of our legs was 4, so that's 4 squared plus 4 squared. That's 16 plus 16, or 32. So our hypotenuse squared is 32. So that is square root of 32, which simplifies. 32 is 16 times 2. Square root of 16 is 4. So we have 4 square root of 2. For this problem, I know that my magnitude, or the length of that vector, or my magnitude, is 4 square root of 2, okay? We have certain notation to use for it. When we talk about the magnitude of a vector, it looks like an absolute value bar. We put the vector name, whether it's V or whether it's, in this case, I think I did name this one V. So the magnitude of vector V, magnitude of vector V, or the magnitude of vector AB, okay, is equal to 4 square root of 2. That's my exact length of the vector. I want it exact when at all possible. So what's happening? Remember in algebra when you found distance between 2 points? That's what we did. We found distance between 2 points. I also could have used the formula for distance between 2 points by going that distance is equal to the square root of the difference in your x values squared plus the difference in your y values squared, right? What is the difference in x values? Was that not our horizontal component? That was our horizontal component squared. Difference in your y values was vertical component, so this is vertical component squared. Anytime at all that you want to find the magnitude of a vector, any vector, I'll call it v, magnitude of any vector v. Magnitude of the vector can be found by taking the square root of the horizontal component squared plus the vertical component squared, because you're squaring each of the legs and adding them together and then taking the square root. Or think about what that meant Pythagorean theorem wise. This was your legs squared being added together, right? This formula can be used for finding magnitude every time. Now think about what we've done in trig recently. In one of our last sections, we talked about polar coordinates. We were given rectangular coordinates. We were wanting to find polar coordinates. How did you find polar coordinates? So, or when you were looking for polar coordinates, okay? So with polar coordinates, we needed the radius r. How did we find r? The exact same way. We went square root of a squared plus b squared, where we had our horizontal, vertical, left, right, up, down distance. That's exactly what we did when we found the radius. It's the exact same thing. It's just different notation. That's all, just different notation, okay? Let's look, those first 5 examples that I did, the 3 examples and the 2 try problems I did. Let's look at those and look at magnitude, okay? So I'll go here. So example 6, these are actually the component form of the vectors from number 4, 5, and 6 that you had in your notes a minute ago. All right. Each of these vectors, we want to find the magnitude. Remember, this value is your horizontal component of the vector. This value is your vertical component of the vector. Magnitude, the notation for that, looks like an absolute value of v. It means the magnitude of vector v. It's the length of the vector. So if I want the magnitude of this vector, I'm going to take the square root, square your horizontal component, square your vertical component, add them together, take the square root. So what do I have here? I have 3 squared plus 4.5 squared. 9 plus, if you square 4.5, don't round, but you'll actually get 20.25. Add that. That's the square root of 29.25, okay? That's the length of the vector or the magnitude of that vector, okay? You're going to use this a lot. If you want, go ahead and try magnitude for all of these, including the try problems we had. Go ahead and pause it. Check yourself at any point. PQ, so magnitude is going to be the square root. This is my horizontal component, so my horizontal component squared, plus, there's my vertical component squared. So that's the square root of 25 plus 81, which is the square root of 106. Simplify if you can. This one won't simplify. Oh, that's not v though, right? I didn't have the name of the vector, so I'll just say the magnitude of vector PQ is the square root of 106. You can estimate it, but that's our exact distance, exact length. Look at this one. The magnitude of PQ here is going to be the square root, your horizontal component squared, plus your vertical component squared. That's going to be 0 plus 49. Square root of 49 is just a nice number 7. Those are the lengths of the vectors. So you're doing what you've done for years, right? And finding distance between 2 points, or length of a radius, or Pythagorean theorem. You're getting that every time. You just don't have to have the sketch to go through and do it. These are always right triangles, form right triangles when you put in the vertical and horizontal distance. Look at this one. So here we have this vector, okay? This was our answer from number 4. This was the component form. This is our horizontal component and our vertical component. So our magnitude is the square root of 6 squared plus negative 4 squared. That's the square root of 36 plus 16, which is the square root of 52. If you can simplify, simplify. 52 is the same as 4 times 13. Square root of 4 is 2. Can't take the square root of 13. So the magnitude of that vector is 2 root 13. This one, square root, horizontal component is 14, so 14 squared plus vertical component is 0, 0 squared. So that's square root. Okay. You can have shortcut there, right? Shortcut. Because 0 is 0. So what you really have is the square root of 14 squared, which is 14. Now you can evaluate 14 squared. That's fine. That's not a problem. It's 196. Okay. But it's a perfect square. It'll even out perfectly. Okay. That's magnitude. Remember, and every single vector has a length, which is called its magnitude, and a direction. Okay, we're going to talk about both. Let's look here. Now, just a note, I'm not going to go through and do a lot with this right now, but when we look at vectors in component form, all we see is the horizontal distance, the horizontal component, and the vertical distance, the vertical component. We do not see where it starts and where it ends. Vectors are considered equal if they have the exact same magnitude, remember that's the length of the vector, and direction. Okay, so if they're pointed the exact same direction. Slope, think about slope of a line. If they all have the same slope, they're moving the same field, except they have to be directed in that same direction in this case. You might have different initial and terminating points, but the length and the direction are the same, okay? You could have an infinite number of vectors that are equal. They do not have to have the same starting point or the same ending point, okay? I could have this vector here, okay? If their lengths are exactly the same, their direction's the same, okay? Those would be equal vectors. Now, operations with vectors, we have two main operations that we do with vectors. One of those is called vector addition, and one is called scalar multiplication. Now, as we go through and work with these operations, you're going to be reminded a lot of what we've done in just an algebra class, really. When you were learning polynomials, adding like terms, subtracting like terms, distributing when you multiplied a polynomial by a number. It's the same sort of thing as you go through and look at. And we're going to do it more of algebraic kind of way to do it, but I'm going to illustrate it for you, graphing as well. When we think about vector addition, okay, what we're going to do is we're going to end up adding their like components. So if you're adding two vectors, each vector has a horizontal component, each vector has a vertical component. Add the horizontal components, add the vertical components, you'll get the component form of your answer of that vector addition. Now, when you go through, and so that's like adding like terms, right? Let's look at this example. We're given two vectors. Vector u has a horizontal component of -1 and a vertical component of 3. Vector v has a horizontal component of -2 and a vertical component of -1. And we want to find u plus v. Now, the way that we are going to focus on doing this is using the idea of the components. When you go vector u plus vector v, you're going to end up with a component form, okay? And in that component form, the horizontal component of the sum of u plus v is going to be the sum of their horizontal components. Add your like components. So I'm going to take my horizontal component of -1, and I'm going to add to it my horizontal component of -2. And in my resulting vector there, I end up with -1 plus -2, which is a -3. For my vertical component of the sum u plus v, I'm going to get the sum of my vertical components, okay? So I'm going to take the vertical component of u, 3, plus the vertical component of v, -1. 3 plus -1 is a +2. So the vector u plus v is in component form -3, 2. That's my answer. Now, that's adding like terms just like we did before. I am going to go ahead and illustrate what this looks like graphically, okay? You don't have to do this graphically. In all of our examples, we'll look at it this way. But just to illustrate what's happening with vector addition, okay? With vector addition, we can use something called the parallelogram law. There are a couple versions of the parallelogram law. With the parallelogram law, what you do is graphically, you place both vectors tail to tail. So you put their tails at the same point. So imagine, I'm going to do it at the origin. It doesn't matter. We don't know the initial point and terminating point. We just know the length and direction. So equal, all vectors are equal, okay, as long as they have the same magnitude and direction. So I'm going to put their tails at the origin 0, 0. And let's look what's going on. Vector u was the vector -1, 3 in component form. That means horizontally, I went backwards 1 unit. There's my horizontal component -1, and up 3 units. So if I started at the origin 0, 0, I went left 1, up 3, I ended up at -1, 3. This is my vector u, okay? Vector v was the -2, -1. This has a horizontal component of -2, a vertical component of -1. What's that mean? If we put the tail at the same point and we go horizontally left 2 and then down 1, we are going to end up the point -2, -1 going that direction. That's my vector v, okay? What the parallelogram law says is Put these tail to tail. Now, to find u plus v, what we're going to do is we're going to finish the parallelogram. We're going to sketch it in. So we have to have sides that are, this side needs to be parallel. Opposite sides need to be parallel. Opposite sides need to be parallel. Notice I sketched in parallelogram. And what you're going to do is, starting at that common tail, go to the opposite corner. Okay, go to the opposite corner. This is going to represent that u plus v. Now, I didn't use graph paper. I didn't do it great to scale here, right? But notice, if I look at that point, 1, 2, looks not too bad. Looks like that's a -3. If I look at my, how far up? Oh, looks like 2. It's like 2. Based on this sketch, starting at the origin, I went back 3, up 2 to get to the opposite side of the parallelogram. This should be horizontal component of -3, vertical component of 2. What was my answer when I did vector addition? It was -3, 2. Same thing, no difference. Which way would you prefer to do, right? These were nice numbers. It wasn't bad to look at a sketch, but I wouldn't want to sketch everything. It would take too much time, okay? Now, before we get into a couple more examples here, we need to talk about scalar multiplication as well. Now, scalar multiplication is when you have multiplication by a constant value, we call that value the scalar, okay? It's going to be very similar to when you use distribution with polynomials. Think about back with algebra. If you had a -3 times x minus 7, what did you do? You distributed the -3 through and went -3x plus 21. You multiplied everything inside by that constant multiple, right? Same idea with scalar multiplication. Anytime you have a vector being multiplied by some number, a scalar, this guy's called a scalar, then what you're going to do is you're going to multiply both of the components by that scalar. So what you're going to end up with is 4 times -2 for the horizontal component, 4 times 7 for the vertical component, which is the component form of -8, 28. That would be the product of 4 times the vector, okay? That's scalar multiplication. So between addition, subtraction, and scalar multiplication, think about your order of operations. What do you do? You always do multiplication before addition, subtraction. Same thing's going to hold with vectors, okay? Let's go on and look at some operations here. Let's look at this guy. We're given 2 vectors. Vector u is the vector -1, 3. Vector v is the vector -2, -1. I'm going to use these throughout 2 or 3 examples here. Let me see if I can get that to clear up a little. Ah, that's better. All right. I want to find u minus v, okay? Think about subtraction. Back when you had arithmetic and you subtracted values, one of the ways you learned it is subtraction is the same as addition of the opposite. Addition of the opposite. So we're really doing a vector addition here. And this -v is really scalar multiplication, because -v, you can think of it as -1 times v, right? So let's think about that. -1 times v would be -1 times the vector and component form of -2, -1. We just saw with scalar multiplication, That means you multiply each component by that -1. So -1 times -2 is a +2. -1 times -1 is a +1. So what we really have here is u, which is -1, 3, okay, plus +2, +1, the opposite of v. And once you get to your vector addition, remember, you add like. You're always going to add and subtract like components, okay? So our horizontal components are -1 and a +2. So I have -1 plus 2. Our vertical components are a 3 and a +1, so 3 plus 1. So that's going to be a +1 and a +4. This is the component form for u minus v. Okay, that's our component form for u minus v. Look at example 13, same type thing. We have our u, we have our v, and we want to evaluate 3u minus v. So what's happening here? We have 3 times the component form of -1, 3, and we're subtracting the component form -2, -1. Always do multiplication before addition or subtraction. So 3 times -1, 3 would be a -3, +9. We multiply. Now you can go plus the opposite like we did back in the last one, but the key is that when you're adding and subtracting, always do the like components. Add and subtract like components, okay? So our horizontal components, we have a -3 minus a -2. That's a -3 plus 2 or a -1. Our vertical components, we have a 9 minus a -1. That's a 9 plus 1 or a 10. So that means that 3u minus v has a horizontal component of -1 and a vertical component of 10. Okay? That's what we have for that one. Multiply is like distribution. Multiply every component by that value. Addition, subtraction, like components. Add, subtract the horizontal. Multiply before you add or subtract. Okay? All right. Keep moving along a little bit. Just a little bit more for this video, and then we'll take a little break. Sorry, paper got a little messed up here. We've already talked about component form, okay? Component form of a vector was what we just looked at, where we wrote a vector with this notation, with the horizontal component first, vertical component second. We have another type of component form that we can use. We call it IJ component form. A little I, a little j. When we think about IJ, I and j are referred to as unit vectors. Vector I is the vector where the horizontal component is 1, the vertical component is 0. Vector j is where the horizontal component is 0 and the vertical component is 1. Every single vector as a horizontal vertical component can be written using these unit vectors I and j. It's just a different way of looking at it. You're not going to have to break down all the work. You'll see the relationship between these guys. But think about what we just did with vector addition. Notice the vector 2, -9. Is it not true? Thinking about the fact that you add components, is this not the same as the vector 2, 0 plus the vector 0, -9. Because how did we do vector addition? You added your horizontal components, and 2 plus 0 is 2. You add your vertical components, and 0 plus -9 is -9. So that's true. And how do you undo multiplication? Divide. What if I think about factoring out? What if I pulled a 2 out of this? What if I made this 2 times 1, 0? Is this not the same? Because 2 times 1 is 2. 2 times 0 is 0. This one, what if I pulled out a -9? -9 times 0 is 0. -9 times 1 is -9. This is the same. So this original vector, which is in component form, is the same as this product. 2 times vector 1, 0 minus 9 times vector 0, 1. Vector 1, 0 is our unit vector I. So this is 2I minus 9, 0, 1 is our vector j. That's 2I minus 9j. This form of the vector is what we call the ij component form. Why do we use the words component in both? Because you still see your horizontal and vertical distances. 2 was our horizontal component. -9 was our vertical component. Look down here. Right there's the 2, the horizontal component. Right there's the -9, the vertical component. In ij component form, the coefficient of I is your horizontal component. The coefficient of j is your vertical component. Every time, it's just another way to write it. So if you know your horizontal vertical component, you can jump to this form of the answer. You don't have to do all the work to get there, but that's where it came from. So coefficient of I is horizontal component, coefficient of j is vertical component, okay? Horizontal, then vertical. Think about them that way. So now you can do your vector addition and your subtraction and your multiplication and everything just as easily. This looks even more like what we did with polynomials. Look for a second. Excuse me. I didn't leave much room for this first example here, but just to illustrate what we just talked about, notice that in this problem we have vector u is 2i plus 3j. In component form, that would be a horizontal component of 2 and a vertical component of 3, okay? Vector v is 4i. I is the horizontal. So vector v has a horizontal component of 4. Now, I don't see a j term. So if I don't see a j, that's like adding 0. I don't have a j at all. That's a 0 for horizontal component. These are the same two vectors in component form. What did we look at just a minute ago? If we wanted to add these two vectors, we added the horizontal components. So we went 2 plus 4, and we added the vertical components, 3 plus 0, and we should end up with, in component form, a 6 and a 3. Okay, that should be the sum of my vectors. In I, this is component form. In ij, component form, okay, this should be a 6i plus 3j. These are the same vectors, just a different look. Well, let's look at it when we were given the ij form, okay? Let's look at this guy. U plus v. My u is 2i plus 3j. So that's going to be 2i plus 3j. I didn't use the, I'm just putting parentheses around to emphasize that we're taking that. And we're adding to it u plus v. V is 4i. So we have 2i plus 3j plus 4i. This looks like adding polynomials to me. 2x plus 3y plus 4x. Same as with polynomials, right? When you go through to do addition, we don't have any multiplication going around, so I can just write this as 2i plus 3j plus 4i, and then you can only add like terms. 2i plus 4i is a 6i. Then we still have the plus 3j. So notice I get a 6i plus 3j. What did I just do a minute ago when I did regular component form? Same thing, right? Didn't matter the form, but we got to our answer. Both of these are accurate ways to write vectors. So this feels just like algebra. So what would we do if we had u minus 2w? My u was 2i plus 3j. Then we have minus 2 times w. This problem, w is negative 3i minus 2j. So I'm taking minus 2 times negative 3i minus 2j. All right. Sorry, they got a little light there, didn't it? So what do we have going on? You have to multiply before you subtract. So I'm going to have to deal with this first. So this is going to be 2i plus 3j. Negative 2 times negative 3 is a positive, so that's plus a 6i. Negative 2 times negative 2 is a positive 4, so that's plus a 4j. Add your like terms. 2i plus 6i is 8i. Positive 3j plus 4j is a 7j. So 8i plus 7j. That would be the vector u minus 2w. Now notice that's ij component form. Component form, that would be an 8, 7. Horizontal component is 8. Vertical component is 7. Okay. Next example, we have 3v plus 4w. What would that be? 3 times v, v is 4i, plus 4 times w, w is negative 3i minus 2j. Again, order of operations, multiply before you add or subtract. 3 times 4i is 12i. Right here, positive 4 times negative 3 is a negative 12i. Positive 4 times negative 2 is a negative 8j. So we would have 12i minus 12i, that's a 0i, minus 8j. You don't need to write 0, that's just a negative 8j. So negative 8j is the sum of those. The horizontal components balanced they canceled each other out basically, right? In component form, that means your horizontal component is 0. They balance each other out, they're 0. But the vertical component ends up being negative 8. Those are the same things, horizontal component, vertical, okay? So in your notes, you have a couple of problems, numbers 17 and 18. Given u equals 2i plus 3j, v is 4i, same vectors. We have 2 more examples, 17 and 18. Notice the difference in the notation here. What did this notation stand for? If you see bars around your W, it's not just vector W. Vector W is this guy here. But the bars around it mean magnitude of W. Magnitude is the length. What did we do for length earlier? Remember, your magnitude is equal to the square root of your horizontal component squared plus your vertical component squared for that vector. So our magnitude of vector W, notice in vector W, our horizontal component is negative 3, Our vertical component is -2. Vertical component is -2. So what we're going to have is the square root, horizontal component is -3, vertical component is -2. So we have -3 squared plus -2 squared. -3 squared is a +9. -2 squared is a +4. 9 plus 4 is 13. Square root of 13 can't be simplified. So the magnitude of vector W, the length of vector W, is the square root of 3. That will be the exact length. If you're ever asked to estimate, it would say round to the nearest 10th or round to the 100th or something like that. Okay. The next one's not quite as straightforward, but it's close. Notice in number 18. This notation, again, refers to magnitude. You see those what looks like an absolute value bar, that's magnitude. So what I need to do is I want to find the magnitude of the vector that's represented by 3u minus v. Okay, I'm given u, v, and w, but I'm not given 3u minus v. So the first thing I'm going to need to do is get what is 3u minus v? Well, that's going to be 3 times vector u, which is 2i plus 3j, minus vector v, which is 4i. So that's going to be, do this multiplication, 3 times 2, that's a 6i. 3 times 3 is a +9, plus 9j, minus 4i. 6i minus 4i is a 2i, plus 9j. So 3u minus v is the vector 2i plus 9j. That means it has a horizontal component of 2 and a vertical component of 9. Whatever's happening from wherever this is starting, whatever our initial point is, we're going to the right 2 and up 9. Okay? Once you know your vertical and horizontal components, now you can do your magnitude. Okay? Now you can do your magnitude. The magnitude of 3u minus v is going to be the square root. Take your horizontal component, square it. Your vertical component, square it. Add them together, take the square root. So that's going to be square root of horizontal component is 2. Vertical component is 9. So that's 4 plus 9 squared is 81. That's an 85. That won't simplify. If it would simplify, you would. So our answer, the magnitude of 3u minus v, is the square root of 85. That is the length of that vector. Okay? So if you have anything that feels kind of strange inside, deal with it first, then do the magnitude. Kind of like order of operations in algebra, right? Do what's inside first, simplify that, then evaluate the outside. Okay? All right. I'm going to go ahead and stop this video here. Practice talking about component form, IJ component form, practice your scalar multiplication, practice your addition, subtraction, all of that stuff with these guys. And then we'll wrap up. In the next video, we'll wrap up this section. Thanks.